Hey team, right. Most of you did well. We all did the dice in class. We pretended the dice were atoms, but I think there were a couple of classes who didn't get the data down. So if you haven't got the data down, here's a chance. If you've already got the data, you can just listen to this again. It's good learning just to hear it again. So in one of the classes there was 42 dice, and we were doing the dice where if you roll an odd number, the atom is decayed. / died. And so after we started, we said that this every time we roll was 10 years. So we started with 42 atoms in this class, and then after one roll it was down to 20, after another roll 10, 5, 2, 0. So a couple of things. What would we expect? We expect, because we've got a 50-50 chance of rolling an odd number, we'd expect to go from 42 to 21. It's pretty close. We'd then go to 10.5, pretty close. We'd then go to 5.25, again, so close, 2.5 or something, and then 1.25, and then blah, 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 blah. So what do we notice? It's pretty damn close to chance. And it turns out the bigger the sample size, the more closer this is going to be to what we'd expect. And when we have a bunch of atoms, we're talking billions of atoms just in a little speck of rock or something. And so it follows what we'd expect. Halving follows it very, very nicely. So if you hadn't already graphed this on your book, the graph goes from atoms left in time, and it's some sort of decay. Now some people will say, well, it never reaches zero. And it does in the end. I mean, even if you're looking at this, it never reaches zero, but it reaches a point where you've only got one atom left, and then eventually the chances of that decaying happen as well, so it decays. So here's the notes. You can pause the video and get these down. Again, I think 2 classes have already got these down, and there's just 1 class that needs to get them. We can read over them again. It's just the half-life is just the time for half of the collection of radioactive types of decay. It depends on the atom, depends on the isotope. Some are very unstable, so they decay very fast. So they decay in microseconds. That symbol there means microseconds. Others take a long time to decay. Uranium-238 has a half-life of 4.5 billion years. And now in our dice, we talked about measured atoms remaining, but it's actually easier, instead of measuring the atoms remaining, to measure the activity or the count rate. So that's to get our little Geiger counter with our buttons here. And here's our radioactive rock. And our Geiger counter just counts how much radiation is coming off. So as the rock decays and there's less and less radioactive material in here, that radiation is going to go down. So it has exactly the same graph of atoms left, the count rate or activity. Looks like this. So in most questions you'll see activity or count rate, but it means pretty much the same thing. Here's an example of how I deal with these questions. They're really easy once you get your head around them. So the half-life of carbon-14 is about 6,000 years. So I just rounded it to 6,000 to make this easier. If the radiation activity due to carbon-14 in the sample has decreased from 1,200 counts to 75 counts per second, how much time has passed? So what I do is I just say we started with 1,200, and then I write down here, after one half-life, how much do I expect? I expect 600. After 2 half-lives, I expect half again, 300. After 3 half-lives, I expect 150. After 4 half-lives, I expect 75. And that's what we're getting to. So 4 half-lives. So how much time is that? 1 half-life we said was 6,000 years. 2 half-lives is therefore 12,000 years. 3 half-lives is therefore 18,000 years. And 4 half-lives is there 24,000 years. Setting it out like this is how I solve these problems. So if there's a problem in a book or an exam, I literally write them out like this and go through them one at a time instead of trying to do everything in my head. So I'd expect you to as well. Cool. Right, so have a go at the questions on page 7.